in that region or near that 4 degree centigrade. So, just to tell you once more, the same statement is that for a given mass of water, or just to write a given mass of water has minimum volume or maximum density at 4 degree centigrade. It's in the vicinity, in the very close vicinity of 4 degree centigrade. And if we want to sort of express this result in terms of you know, a figure, it can be shown as this. So this is the volume of, so the volume of 1 kg of water. So, and this is in 10 to the power minus 3 meter cube, and this is my temperature scale, and this is in in degree centigrade. So what happens is that the volume actually starts decreasing, as I told you, and then it starts increasing at this. So it decreases from a 1.00013 to a value which is 1, exactly at 1 with that many decimal points, and rises to about 1 point, I'm writing it here, 1.04343 at about close to maybe, so this is close to 100 degree centigrade. So this is not drawn to scale, so I'm breaking the scale here, and also probably a breaking of a scale is needed here. So this is 4 degree centigrade, and this is 0 degree centigrade, and this is around maybe 10 degree centigrade. Well, degree centigrade is written, so this is like 0, 4 and 10, and this 100 degree centigrade. So at 4 degree centigrade, the volume of water is minimum, which touches a value which is equal to 1, so that it is the value is equal to 1 at 4 degree centigrade, while the value is at 0 degree centigrade, it's 1.00013. And as a result, if you draw the density, and the density will also go from some value which is and will go like this, and this is at 4. So this is again at T in degree centigrade, and this is density, and this density has a value exactly equal to 1, and it increases from a value close to, very close to 0.99985, and reaches, so at 0 degree centigrade it's 0.99985, and it reaches a value 1, exactly equal to 1 at 4 degree centigrade, and say this is something about 10 degree centigrade. Okay. So this is pretty much the behavior of water, and this is called as the non-monotonicity. So this is non-monotonic, it's not monotonic. Monotonic means either it's increasing in the range that we are talking about, or it's decreasing in the range that we are talking about, while this has a dip here which shows a minimum here, or which translates into a maximum here in the density profile as the temperature is varied. Now why, as I told, this is very important from marine life, and why is it so? So let us try to understand. And so basically in marine life, particularly in countries which are near the poles or which are very close countries, as I told, Canada is one of the coldest countries, and there this problem is quite important. So what happens is that when the air temperature drops, especially in the winter season, the surface of the air gets chilled, okay? And suppose the air temperature is still above 4 degrees centigrade. So the surface level of water gets chilled, it becomes heavy, and it goes down, okay? And the level below comes up, and you know, that gets again comes in contact with the air, which is cold but still above 4 degrees centigrade, and this process continues till all the water reaches a temperature of 4 degree centigrade. Okay. Now, say during night time or when temperature falls below 4 degrees centigrade, then or reaches say 0 degree centigrade, then the upper layer freezes. So this upper layer freezing has an impact on the layers that is below. So this frozen layer or the layer of ice acts as an insulating sheet for the heat to percolate down or go down to the layers, to the water layers or the water below. Okay? And between, as we told, that between 0 and 4 degrees centigrade, the density of water is maximum. So this level, which is at 0 degree or between 0 and 4 degree, will, the density being maximum, will stay on the so it basically it doesn't sink. So farther cooling below 0 degree centigrade, below 4 degree centigrade, makes the surface layer to be less dense than the layers below. So since it's less dense than the layers below, it will float on top, and also importantly, this layer of ice or the frozen water acts as an insulating sheet for the heat not to be able to percolate down to layers below, and hence the marine life will survive without the entire lake frozen. So the top of the lake will be frozen with a certain thickness of ice being formed on the top, and the rest of the water is still maintained at 4 degrees centigrade, making it possible and convenient for the marine life to survive. So, and it's, as I said, that it's possible because of this particular anomalous behavior of water that happens between 0 and 4 degrees centigrade, in which the volume contracts upon heating between 0 to 4 degree centigrade, and beyond that, as I said, that it acts normally. So having talked about this heat and properties of heat and temperature, and the concept of thermal equilibrium, and the concept of thermal expansion of solids, mostly solids, and now we have talked about thermal expansion of liquids. It is important to understand the one concept which is called as a specific heat capacity, and this is all what you have learned in your school level, that the specific heat capacity is defined as the amount of heat required to raise the temperature of a body by 1 degree. And so it is understood that a greater amount of heat is required to raise the temperature of a substance to higher values. So the amount of heat is proportional to two things. So let us change the title here and let's talk about specific heat capacity. So the amount of heat Q, let's call it Q, is proportional to one mass of the substance and the temperature difference. So mass of the substance is m and the temperature difference is delta T. Okay. So Q is proportional to m and delta T. So delta T is, as you understand, it's T2 minus T1. So T2 is the final temperature and T1 is the initial temperature. And so Q can be written as proportional to m and proportional to delta T. So Q is equal to some C m delta T, where C is the proportionality constant and is called as the specific heat capacity. Which of course has a value, or rather the SI unit is expressed in joule per kg degree centigrade. Okay. So the heat is expressed in joule, the mass is expressed in kg, and the delta T is expressed in degree centigrade. So this has a unit which is joule per kg degree centigrade. And just to quote some values for the specific heat, to have every time we quote a value is to impress upon the fact that you should know some representative values of substances that you are exposed in everyday life. And so we are talking about specific heat capacity of some solids. And well, solids, and I'll also club liquids, it's only the gases to be treated separately for the reason that I'll come to in a while. And so solids are, so materials, solid materials are so it's aluminium, so C is 9, so this is in joule per kg. So this is 900, copper is, so these are for solids, copper is 387, glass, again it's Pyrex glass, it's 840, and iron is 452. So these are for the solids, and let's also write down some liquids such as water at 15 degrees centigrade. So this has a value which is 4186, mercury this is let me check the number. Yeah, so this is 4186 and mercury is 139 and the glycerin is 2410. Now this number might be confusing to you, and this is nothing but it's equal to 1. It's equal to 1 when you write it in terms of 1 kilocalorie per kg degree centigrade. Okay, so this is we are very familiar with, whereas this for water at least we are not too familiar with the joule per in the units of joule per kg degree centigrade, but this is equal to 1 kilocalorie per kg degree centigrade. So this is for the specific heat capacity for solids and liquids, and the gases need a special mention for the reason that you need to mention that whether you are keeping the gas at constant pressure or at constant volume. Now this question does not make too much of a difference when you are dealing with solids and liquids. For gases they definitely make a lot of difference. So we'll call the specific capacity for gases of gases, and so specific heat capacity C at we denote it by this letter C at constant pressure is, let's call it as Cp, and C at constant volume call it as Cv, and some representative values again for certain gases which are very familiar to us. So a gas and its Cp again in joule per kg degree centigrade, and Cv joule per kg degree centigrade. And so a nitrogen which has a Cp of 1040, whereas a Cv of 39, that is a specific heat at constant volume as 739. Carbon dioxide, which is as you all know that it's denoted by CO2, this is equal to 833 and this is 638. So and water vapor at 100 degrees centigrade. So we're not talking about water, but we are talking about water vapor at the steam point, which is equal to 2020 and 1520, and oxygen, let's write it with O2, it's equal to 912 and 651. So one important thing that comes out is the fact that your Cp is always greater than Cv. Thus the specific heat capacity, which appears as a proportionality constant for the amount of heat required to raise the temperature of a certain mass of a substance, or here the gas, by a temperature, through a temperature difference of delta T. So that at constant pressure is always greater than that at constant volume. And as I said, that it doesn't make a difference for solids and liquids, but it makes a difference for the gases. And as you can see that the numbers are quite different. They are really quite different. And in order to understand this, you'll have to wait till the thermodynamics chapter, where you learn that there is an additional amount of work that is done at constant pressure, which creates a change in volume, and that's why your Cp is always greater than Cv. And there is a relationship between Cp and Cv, which can be derived for a gas which is either a monatomic gas or a diatomic or a triatomic gas. All right. So we have looked at a number of things, including the heat capacity, the thermal expansion properties, anomalous expansion of water. Then we talked about the temperature scales, their interrelationship between a Celsius and a Fahrenheit scale, the Kelvin scale of temperature, and most importantly the concept of absolute zero, and from there to get a gas law out of it, which is P is proportional to T, or P by T is a constant. Let us look at some of the important temperature values which one comes across in different branches of physics, so that you have a ready reference of some numbers in front of you. So these are mainly for your information, but they are quite useful at times, or when you are trying to read a journal or a paper or a newspaper, and when these numbers are quoted, then you know that what they mean. So, so a temperature, now I am expressing it in Kelvin, and a phenomena which are very important and have consequences in different branches of physics. So a 4.2 Kelvin is when helium liquefies. So it's the liquefaction temperature, or when the helium gas is converted to a liquid helium. That's the temperature. I've forgotten to say one thing, that is the constant volume gas thermometer that we have discussed, the glass bulb that we have drawn earlier, the gas contains is usually a lighter gas, which is either a hydrogen or a helium. So and the liquefaction temperature is 4.2 Kelvin. So I'll not write the Kelvin here, I'll simply talk about this and just the numbers. So 20 Kelvin is when hydrogen liquefies. Hydrogen liquefies. Interesting that hydrogen also can be liquefied, and there's a liquid hydrogen available, which happens at 20 degree Kelvin. With 20 Kelvin, you'll have to be correct. It's at 20 Kelvin. 20 Kelvin, as you understand, is far below 0 degree centigrade, which is the freezing point of water, or the ice point, as we say. As I told you that for scientific importance, which are beyond our day-to-day needs, or the daily input, is usually restricted between 0 degree centigrade and 100 degree centigrade, or 32 Fahrenheit, 32 degree Fahrenheit to 212 degree Fahrenheit. Whereas there are temperatures which are of importance, scientific importance, which are much below that or higher than that. So 77 is when nitrogen liquefies. If you have gone to a sort of science museum which has a liquid nitrogen show, they usually project it as a show in which liquid nitrogen is seen to coming out from a container, making fumes out, which are very cold fumes, and do not ever try to put your hands into that. Because these temperatures are very cold. It's 200 degree below below the ice point, and anything that comes in contact, you have to be very careful in handling those temperatures. And so that's when nitrogen liquefies. That's a liquid nitrogen that is shown there. And in fact, in some of the movie shows or some of these television serials, when they show that, a lot of smoke is actually coming out, and it's not hot smoke, it's really the smoke coming from the from the liquid nitrogen. 273 Kelvin, all of you know that water freezes, which is 0 degree centigrade. For your ready reference, I'll use this. So water freezes here. 310 Kelvin is human body temperature. As I told you, the doctors will never tell you 310 Kelvin is the body temperature that you have, or you have a little more than that if you have fever. They'll say that it's over and above 98.6 degree Fahrenheit, or in some exceptional cases they'll talk about 37 degree centigrade, which is a normal body temperature, but it's not usually quoted in terms of Kelvin. 373 is when water boils. Uh, 600 when lead melts. So melting of lead, which you see in the at the end of the edges, end of the pencils, that melts at 600 Kelvin, which is much beyond 100 degree centigrade or 200 degree Fahrenheit. So 6000 is the surface temperature of the sun. Uh, 16,000 Kelvin is the core temperature of Earth. Uh, 10 to the power 7 Kelvin is the core temperature of sun. And 10 to the power 9 is the core temperature of the hottest stars. Okay, so these are some of the temperatures which are usually you would see in scientific articles and scientific journals. So these are really large temperatures, and we are talking about the hottest stars and not like the white dwarfs which are nearly gone. When you read about stars, and then you would know that the content of stars is really the helium gases which are always burnt in order to make the stars glow, but some of these stars have the entire content of helium nearly used up, and they are no longer they're nearly like dead stars. White dwarf is an example of such things which are usually taught at higher level. So we'll not elaborate on that. But these are starting from 4.2 Kelvin, close to 0 Kelvin, all the way up to 10 to the power 9 Kelvin. There are different phenomena that are important scientifically. To remind ourselves, we were discussing thermal properties of matter, and we were particularly talking about specific heat capacity. And the way it was defined is that the amount of heat that is required to heat up a substance and thereby causing a change in temperature is proportional to the mass of the substance and is proportional to the change in temperature that it induces because of the addition of heat. So if you write this with an equality, we would need a proportionality constant which is called as specific heat capacity, which depends on a particular material. Now let us look at how specific heat capacity is measured. So specific heat capacity is measured by an apparatus called as calorimeter. So what is a calorimeter? Calorimeter is essentially an apparatus like a thermos, which you have seen where hot coffee or hot tea is stored, especially in offices, which is having some kind of insulating wall and so there is an insulating wall outside, and there is an inner space where there is a particular substance is kept, and one can measure the temperature by using a thermometer, such as a mercury in glass thermometer that we have talked about earlier. So there is a fluid here. So there is a fluid here whose temperature can be measured by using a thermometer. So this thermos or the calorimeter does not allow heat to leak in or heat to come from the surrounding to inside. However, if there are 2-3 substances that are kept in this inner flask or inner container, then the flow of heat is possible. Flow of heat is possible provided there is a temperature difference between the two, between those constituent substances. So even though heat is not coming in from outside, heat in the form of energy can flow from one substance to another, such as if one has kept tea and ice cubes, then according to law of conservation of energy, heat will flow from the hot tea to the ice cubes, and finally if one waits for long enough, an equilibrium will be achieved in the system. So this is by and large the apparatus, and let us see through an example how this apparatus can measure the specific capacity of an unknown substance. So let us do this by a numerical example. So we'll write down the problem. So it's an example problem. So, in an experiment, to find the specific heat capacity of a metal of mass of a block of metal, say block of metal of mass 0.2 kg at 150 degrees centigrade is dropped in a copper calorimeter, is dropped in a copper calorimeter whose mass is let's call it as the mass of the calorimeter it's equal to 0.25 kg. Sorry, the mass of the calorimeter is taken as 0.14 kg. And this calorimeter containing water or 0.25 kg water at 27 degrees centigrade. The final temperature so this final temperature means that after the thermal equilibrium is established. So the final temperature is 40 degree centigrade. Compute the specific heat capacity of the metal. It is given that I'll use a shorthand notation now. The specific heat capacity of water, so we'll call it as CW. This is equal to a 4.18 into 10 cube joule per kg Kelvin, and the copper calorimeter has a specific heat capacity. I'll call that as C. C stands for calorimeter, W stands for water. So this is equal to 0.386 into 10 cube joule per kg Kelvin. Okay. So just to summarize the problem, that we want to know the specific heat of a certain block of metal. So a 2.2 kg block of metal is dropped into a copper calorimeter which has mass 0.14 kg, and this calorimeter contains 0.25 kg of water at room temperature, which is usually taken as 27 degrees centigrade. Once this is dropped, the block of metal was initially at 150 degrees centigrade. So after the thermal equilibrium is achieved, that is, heat will flow from the hot block of metal to the cold water. After the thermal equilibrium is achieved, then the final temperature is 40 degrees centigrade. So, using these data, one has to compute the specific heat capacity of the metal, and it is given that the specific heat capacity of water is this, and the specific heat capacity of the calorimeter, copper calorimeter, is this. Okay. So, I will remove this for now in order to do the problem. So, the basic principle is that the heat that flows out of the metal block is absorbed by the water and the calorimeter. So, these two quantities of heat would be same in order to compute, and one has to compute the specific heat capacity of the metal. So, let us write, so M, so data given, mm, which is mass of the metal, is equal to 0.2 kg. So, the so initial temperature of the metal, let us call it as Tm1 equal to it is 150 degrees centigrade, and Tm2, that is the final temperature of the metal, would be same as the final temperature that is quoted here, which is 40 degrees centigrade. All right. So, delta T, this is equal to Tm1 minus Tm2, which is equal to 110 degrees centigrade, and since 1 degree centigrade is same as 1 division in the Kelvin scale, Kelvin temperature scale, we can just simply call this as 110 Kelvin. That is the temperature difference, the initial temperature minus the final temperature. So, the heat lost, by the metal block so Qm it's equal to Cm, which I need to find. M is 0.2 kg and my delta T, which is so that is my the heat required. So, this will be in joule. So, this is like 22 cm and in joule. Now, so this heat is lost by the metal block. Now, it has to be the same amount of heat has to be gained by the water that is present and the copper calorimeter. For the temperature difference for both calorimeter and copper is so delta T for which is for water. So, this is for the metal. So, this is 40 degree centigrade minus 27 degree centigrade, which is equal to 13 degree centigrade, which is nothing but equal to 13 Kelvin. The specific heat of water is given. So, the amount of heat gained by the water plus calorimeter. So, QW plus Q calorimeter, this is equal to MW CW delta T, which is so this is W water and the calorimeter. So, this is let us just call it simply as delta T, and plus M for the calorimeter, C for the calorimeter, and the same delta T. So, this comes out as if you do this simple algebra, it comes out as 13.585 plus 0.703 into 10 cube joule with the data that are given here. So this is the heat gained by the water that is kept in the calorimeter and the copper calorimeter itself. So my, let's call this as Q total, so QT. So according to the principle of calorimeter, so Q total should become equal to Q metal, and if I equate equation 1 say to equation 2, I will find Cm to be equal to 0.649 into 10 cube and joule per kg inverse Kelvin inverse. Okay. So this is the specific heat capacity of the metal block that is needed to find out, and the calorimeter finds out, is the apparatus which finds that out. Okay, so so this way, for any unknown liquid, the specific heat capacity can be determined. Now let us look at another very interesting phenomena which is called as change of state, and how a change of state is actually accompanied by the latent heat. So we'll have to understand the concept of latent heat. The word latent means sleeping or dormant, or which is not perceivable or observable. So we know that there are three states of matter which we are continuously talking about in various contexts, which are solid, liquid and gas. And they have their own properties that we have seen. There are values of different quantities, physical quantities, we have seen their experimental values and so on. Now one can actually achieve a change of phase or a change of state, that is one can go from one state of matter to another state of matter, either by addition of heat or by removal of heat. And this change in phase is possible in a day-to-day experiment, and this will be accompanied, as we will discuss soon, will be accompanied by a latent heat. So normally we understand that when we add heat or remove heat from a substance, the temperature would rise or fall depending on the situation. Now there are situations in which the temperature does not rise or does not fall even if heat is added or removed. Let us take this example of say this is a thermos flask, and there are iced tea. So there is iced tea, tea plus ice cubes, which are known as iced tea, say for example. So there is tea and there are ice cubes there. Now what you do is that you put it under a flame. So you are heating it up. You are heating it up, and this is just a container, or it could be, you know, a sort of a flask that we have said. It's just a container for now. And one is heating it up. What will happen is that and if you have a thermometer somehow that you can insert it here and record the temperature, you will see that there is no change in temperature for some time, and that some time is till all the ice cubes melt. When all the ice cubes melt, it will be only tea remaining there in liquid form, and the heating more the temperature will start rising again. Okay? And so apparently the purpose of the heat is not to increase the temperature, and the temperature remains at 0 degree centigrade. So just to summarize it once more, that you have some tea there and ice cubes that are kept in a container, and you have started heating it up, and you're measuring the temperature, and you see that heating for some time, the temperature does not rise, and the mercury or the reading of the thermometer stays at 0 degree centigrade, which is the freezing point, or which we have called as the ice point. And when all the ice cubes melt, then only the temperature starts rising. So in that intermediate phase, when the temperature does not rise, the purpose of heat is actually not to increase the temperature, but to do something else. And that something else is in the form of melting the ice. And if I want to draw this as a plot for so temperature in degree centigrade and time, which time could be measured in minutes or seconds depending on how much of ice tea we have, or rather tea and blocks of ice. So we leave that unit for now. So what we'll see is that for some time the temperature does not rise, for some minutes or seconds, whichever unit we are measuring it, and then it starts rising, and then what happens is that it will be again there is a plateau. A plateau is a flat line, and which happens at 100 degree centigrade. Well, we have written degree centigrade, so this is 0 and this is 100 degree centigrade, and then it starts rising again. We have simply just talked about this part where the temperature does not rise. We have not talked about this plateau, which we are just coming in a while. Now also have a look at this diagram here. We can now erase this, that we have three. So let's draw a slightly bigger equilateral triangle. So at this vertex of the equilateral triangle, we have a solid. So this is a solid, and there is a container containing a liquid, and there is another container containing gas. Okay? So these are the three states of matter, and one can go from one state to another, just like what we have seen just a while back, that the ice cubes upon heating are melting and becoming water, and that's the so a solid is becoming a liquid. So these processes, let us name these processes before we go ahead. So these processes is called, this is called melting. It's also called as fusion. In some books you will see them as fusion. This is called freezing. So when you keep water in the deep refrigerator, where in a part of the fridge which makes ice, that is where when a liquid is transformed into a solid ice. And this is called as evaporation. So conversion of liquid into its gaseous form is called evaporation, and the reverse process is called as condensation. Similarly, this from solid to gas directly, which is not very common, even though some materials show this property that directly from the solid phase it goes to gaseous phase. Camphor is one such example. We will give another example, interesting example. This is called as sublimation. And the reverse is again called as condensation. That is, going from a gaseous phase to a solid phase is called as condensation. So what happens in this part is that the water starts to boil, because now from here we had at this point, let's name them, let's call them as A, B, C, D and E. In this part ice melts, and what happens to this? So this AB part, the ice melts. In this part the water warms up. Water warms up, and the heat required, or rather the heat needed for the water to warm up, will follow this equation Q equal to mc delta T, where Q equal to the heat, m is the mass of the substance, and C is the specific heat of the substance, and delta T is the temperature difference. Here the temperature difference is 0 and 100 minus 0, which is 100 degrees or 100 Kelvin. Then here what happens in this part, that is this part CD, is that the water boils, and again the temperature does not rise. Again the temperature does not rise, and even if heat is being given, because we are scanning it as a function of time, which means that we have put a burner or a flame and subjected the system to that flame. So it's the heat is continuously getting into the system, or its heat is added to the system. Suppose we are going from increasing in time, or if you actually also want to call it as heat, and in which case we can also talk about removal of heat if we go from the right to the left. But right now we are going from the left to the right, and here water boils, and the water will boil till the point that all water is converted into vapor. When all water gets converted into vapor, with the addition of heat, the temperature then starts rising once again. So it's basically water vapor warms up. Okay. So I hope this figure is clear. We've drawn temperature versus time, time over which this system is subjected to heat. This part, the temperature does not rise, and the system undergoes from a solid to a liquid phase. So all the ice melts. When all the ice melts, the temperature starts rising again. Now at this point water starts boiling, which means the system now is a combination of liquid and vapor, and when all the liquid gets converted into vapor, then the temperature starts rising once again. So this is typically phase diagram, or rather the showing of different phases when a change of state or a change of phase occurs due to addition of heat. We can also talk about, as I said, that removal of heat, in which case we actually move in the reverse direction.